Okay, hello. Good evening. Let me first recall what we did last time. We started discussing recurrent neural networks. That means networks that have memory. So the situation is depicted here. You would have as input to your network a time sequence. And so maybe at some point in the time sequence there's a kind of signal. Then for a long time there are no important signals. And suddenly there's another signal that now references back whatever the network received in earlier time slots. So the network really needs a memory to reply to this challenge. And a typical example would be if you tell the network some story, which is a sequence of words, and then at some point you ask a question about the story and it has to reply, and then obviously it needs a memory. And so the solution are these recurrent neural networks, where you can imagine that here you have the input, so each of these blue circles could, in the simplest case, be just one value, one input neuron, and then the blue circles labeled output would be also just one neuron, one value. But in a more complicated setting, each of these blue circles could be a whole layer of neurons. And then what this depicts is actually the progression in time. And so the network really doesn't change. The network would just be this combination, in this simple case, of input and output neuron or input and output layer. But I draw it several times. So at each new time step, I again draw the same network. And the reason I do this is because I want to be able to depict how the network keeps memory. So how it keeps some of the values of an earlier time step influencing the calculation of the values for the next time step. So here the slide just depicts that each of these blue circles in reality can be a whole layer of neurons. And of course we can also play the same trick as before. We can have hidden layers. So now there would be the network would consist of an input layer, a hidden layer, and an output layer. And I draw many, many copies of the network corresponding to the different time steps. And of course, for each different time step, the input is different. So that means all the values in the whole network will be different, even just for this reason alone. Plus also the memory it receives from earlier times will of course be different. And that also can make the output of the network different. So the question is how learning proceeds. And again, and the principle is the same as usual, you will have the correct answer that you supply to the network together with the input, and then you want to make sure that it comes closer to this correct answer. So here I depicted a situation where inputs are given during all the time steps, but the output is only read out at the very final time. And then the correct answer is known, the correct output is known. Maybe your true output of the neural network deviates from this correct output. So you calculate the deviation and you try to minimize this deviation by taking the gradient. And that means really what you want to do is you want to adapt all the weights in the whole network in order to get the right output. And so when you now do backpropagation, not only do you have to take gradients down towards the lower layers in the network, that was the case all the time already, but also when you calculate these gradients you have to go back in time because the output of earlier times influences the final result. And so you have to try to adapt all these weights. Now there's a funny thing here. Remember, this is not, 10 different networks somehow connected together. It's only a single network which I draw repeatedly for the different time steps. So that means the weights are the same for all the time steps. The weights do not change in time. And that means if you find out during your backpropagation that you should change this weight a little bit in some particular direction, but here you should change the weight in some particular different direction, what you will end up doing is actually changing the weights that belong to this particular arrow that connects the hidden layer and the output layer, you will change them according to the, say, average or the sum of all these proposed changes. Okay. So now there was a fundamental challenge here, and that was the exploding gradients or vanishing gradients problem. So that occurs not only for backpropagation through time, but in principle also if you have a network with many, many layers and then you want to backpropagate down from the highest layer, from the output layer down to the input layer. And so what can happen as depicted is graphically summarized here. So this deviation vector that you change during backpropagation by multiplying it with one matrix per step, that could end up exploding or vanishing, which in qualitative terms has a very simple meaning. It means that either the changes that you implement to the weights here have no influence at all on the output, so you can try everything you want, but you don't see any change, or these weights that you change here have a dramatic influence on the output, so either way is not good. Okay, and so that led people to a solution that is called long short-term memory. And I explained it last time, but I repeat it. So the long-term memory of a neural network, that would be contained in its weights, because that's what you change during training. After you go through the 100,000 training examples, these weights have been updated, and in those weights, the network keeps a long-term memory of anything it has ever trained on. So that would be real long-term memory. What we are talking about here is rather short-term memory. So you have a task, you get a small time sequence of, I don't know, 100 time steps, and you have to remember what came at the beginning of this time sequence and be able to recall it at the end. So that for humans we would call this working memory. And it is this short-term memory which we want to make as long as possible. So that's why it's called long short-term memory. And so what these people realized, Hochreiter and Schmidhuber, is that you want to avoid this problem of vanishing or exploding gradients. And their idea was maybe you can do it such that you read out the memory cells only very rarely, namely when you understand that you should read them and exploit the readout. For example, only if someone asks you a question about the story that you just heard, that's the time when you really need to read out. During all the other times, you should not access the memory cell. And as we will see in a moment, this really helps with this vanishing or exploding gradient problem. Okay, so the idea again is you shouldn't at each time step take whatever is in the memory cell and supply it as an output. You should only do this in particular time steps. So you need some way to calculate whether you want to do this operation, whether you want to read or to write or to delete. And I want to show it first for the very elementary operation of deleting the memory cell. Yeah. So in this notation, let me say the content of my memory cell I call C. So now imagine this is a single neuron. It carries a value C. That's the memory it stores. That's the value of this neuron. And I go from time step t-1 to time step t. So I go forward one step in time. And now I have to decide whether I want to keep the memory or whether I want to forget. And so mathematically I could represent it like this. If I want to keep it, then the new value, ct, should be equal to the old value, ct-1. But if I want to delete it, then the new value should be simply 0. In other words, I can always multiply the old value by some factor, but the factor will be 1 if I want to keep it, and 0 if I want to delete it. Yeah? And now this value is not externally given, but I want to calculate it. I want to calculate it based on the values of some other neurons. For example, based on the input. Yeah? Depending on what I see around in my environment, depending on what input my neural network receives, I may want to forget what is in the memory cell. And so the way this is done is you would have your input neuron that has some value, let's call it xt at some time t. And I take this value and I send it to another neuron where I calculate a new value f. And this value f will then tell me whether I want to keep or delete. So this value f is the factor with which I will multiply. It's either 1 or 0 or maybe something smooth in between. Yeah? So I will calculate such a factor. Now, how do I do this? How do I calculate the f based on the input? Well, that is shown here. That's the standard situation. I maybe would take the input, multiply with some weight, add some bias, take a sigmoid function that nicely lies between 0 and 1, and I get my value of f. The good way of writing it in this way is also I can now generalize easily. If my input consists of many input neurons, as it will be in many neural networks, then I could also have many forget gate neurons and many memory cells that I will consider. And then you just need to generalize this by saying W is a matrix, B is a vector, X is also a vector as usual. Sigma acts element-wise on the resulting vector, that is its argument, and then F also will be a vector. So you see all of these things can be easily generalized to many neurons. But you can also think for the moment of just a single neuron. And then once you've calculated F, you can immediately calculate what's the new content of the memory cell. So you just take the old value, you multiply it with F. Okay. And so this is a funny moment because for the first time now we are really multiplying neuron values. So both the CT-1 and the F, they are values of a neuron, and we are multiplying them to get a new value of a neuron. So this is a little bit different from what we did before. So that now means something interesting for backpropagation. If I want to take the gradient of this memory cell at time t, CT, if I want to take the gradient with respect to its argument, or if I want to take its gradient with respect to some weight that sits somewhere earlier in the network, then this gradient will have two contributions because there's a product. So I take now the gradient of a product, and of course there's a product rule. So if the new memory cell content is f times CT-1, then taking the gradient of this splits into two parts. Once I take the gradient of f, and the other time I take the gradient of CT-1. That's just the way it is for the product. So that means in a graphical language, I split my backpropagation into two paths. One will propagate down the network here, down towards these other arrows that may contain some interesting weights, and one path goes just back in time. But that's okay, and in fact this can be handled by backpropagation, and as usual these days you don't even need to implement this yourself, because something like Keras or TensorFlow will do it for you. But in principle, this is what happens behind the scenes with the backpropagation. So now, just to give the whole illustration, if I draw several time slots, then this forget gate and this deletion operation will act in each possible time step. And so I have to keep track of all of that. Okay. Now this was just deleting. Now the next thing is writing, and then of course there will be reading. If I want to write a new memory value, then not only do I have to decide whether I want to write, but I also have to decide what should be the new value. And so again, this works similar to before, only a little bit more complicated. Here's my input value. I will use it to calculate both a potential new value and the value of this input gate. And now what I will do, so here's written how I will calculate these new values. And now I can do the following. I take the potential new value, I multiply it by this input gate, I add to that the old result from the forget gate, and that is now my new value of the memory cell. So for example, I could decide to completely forget and only write in a new value. I can also decide to keep it, so f equals 1, and just add a new value. That can be very useful, obviously, if you have something like a counter that in each time step adds a new value. Yeah? So then, for example, there might be cases where it's really useful to integrate an input function, yeah? to add up the values over time. This could be very easily realized in this way. Yes, please?
Is it important that the activation function here for CT is different than for I? I mean, they're nonlinear anyway.
Oh yeah, sorry. So I'm just giving you the original version of this, but of course there are many other possibilities that you can take. Certainly the C tilde, that could be a ReLU function, if you like.
Could I choose the same function?
You could also choose the same sigmoid in both. Mm-hmm. Good. Okay, so you now see the game. Yeah, there will always be a gate that decides whether I want to do this operation. And then finally the read operation or the output operation. This is when we decide whether we really want to pass on the value that is contained in this memory cell, whether we want to pass it on either to the next neuron layer or to the final output that can be processed further. Yeah? And this, again, not surprisingly, is done by something that's called an output gate. So the actual output, here called H, will be this output gate value O times some value of the memory cell. Okay. And so it is at this stage that we could, for example, decide most of the time that we actually don't even want to pass on the content of the memory cell to the outside world. In which case also we are safe against the backpropagation. Okay. So now there's one more thing. So there's a little catch here, which can be solved by this additional step. So you want to make these gates not only depend on the input, but also maybe on the previous output that has been calculated in the earlier time step. Because you might want to read something from memory in one time step and use that value to decide what you want to do in the next time step, whether you want to delete something or output something and so on. And this would not work so easily if you didn't have this extra step. So now, instead of what I showed, which was kind of the simplified version, I will say that my forget gate not only depends on the input that comes from the outside, but also it depends on the whatever we read out of the memory cell in the previous time step. Okay. And so now I come back to the backpropagation. So the claim is, as long as we don't do anything with the memory content, we are safe. Yeah? So we don't have this exploding or vanishing gradient. And it's actually very trivial. As long as we don't do anything, CT equals CT minus 1 equals CT minus 2 and so on. Yeah? So they are all the same. So if I now take a gradient with respect to any parameter, like some weight somewhere in the network, then these gradients are all the same. In other words, I'm just multiplying by a factor of 1. Where I had previously this ominous matrix M, which could then lead as a factor to explosion, I just multiply by 1. And so this is what helps in this game. Okay. So now that was the structure. As far as neural networks go, in comparison to what we learned so far, this is probably the most complicated. But that's okay. Because when you use something like Keras, you can easily implement it. And all these little details like the forget gate and the output gate and blah, 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 you don't even need to care about. They will happen behind the scenes for you. And so, for example, if I decided I do have a time sequence and I want to try LSTM for processing this time sequence, I will just do the following. Instead of just making a neural network that has one dense layer stacked after another dense layer, or maybe several convolutional layers, I will just say this, that please give me an LSTM layer of 10 neurons, and then I will have an LSTM layer. And internally it will have all these forget gates and so on, but you don't need to care about them. And each of those can contain their own weights and so on, and they will be updated during training, but you never need to look at them, or you never need to care about them. Okay, so some little detail, now that's going into the syntax. In something like Keras, you can decide whether in such an LSTM you want to get the full time sequence of output values, or you only are interested in the output value at the very last time step. So there are good applications for both cases. And so here I have the full example application where I want a network that has 3 input neurons, then an LSTM layer with 5 neurons, and another LSTM layer with 2 neurons that also serves as the output layer. And so the way I would initialize it in Keras is the same as before. I say I want the standard kind of neural network, which is called a sequential neural network in Keras. But now when I add the layers, I add LSTM layers. And so here you see these. What else is there to tell? Oh, maybe one thing. The input shape for such an LSTM thing is now a little bit different because you want to pass into the LSTM a full time series. So there must be a place where you tell it how many time steps will this time series have, and that's actually given here. The 3 would refer to the 3 input neurons. And the none here in the first slot, that just means there's also a slot for the batch size, because you can still work with batches, but I don't specify in advance how large are these batches. Okay. And so now I want to give you an example, because an example is very helpful here. And we will go through the code in a moment. So I basically want the network to memorize something. And that means, let me just assume I have 3 input neurons, because it makes it easier to set this up. So here are the 3 input neurons, 0, 1, 2. I plot them above each other. And then to the right, I have time running. Now, I want one of these neurons to play the function of indicating the time when I want to tell something to my network, when I wanted to memorize something. And so only at this point in time it will be 1. And then neuron number 1, input neuron number 1, will contain a value, and it is this value that I wanted to memorize. And then at a later time, I want to tell my network, now please output that value that I told you much earlier. And so here I just take another neuron that only becomes 1 at this particular point in time. Okay. And so now, what would be the desired output time sequence for this case? Because that's what we want to do. I mean, I'm telling you the function of these neurons, but it's not something that the network gets told. The network must figure this out on its own by looking at many examples. So here's the desired output time sequence for this particular input time sequence. And nothing happens most of the time, except at this particular point in time where we want the network to recall, and then the output should be 0.4. Maybe at other times the output should be 0, I don't know, something that we decide. Yeah? And so now the way the network learns is, I will show it not only this one particular example, that wouldn't be enough, but I will show it 1,000 examples of this sort, always with randomly chosen points in time where I tell it something, randomly chosen points in time where it has to recall something, and also random values that have to be stored in memory. And then slowly, by comparing against the correct expected result, it will figure out what we expect it to do. That's the fun. Okay, let me now switch to the actual code, just so you see how this works. Okay, so here I'm already using TensorFlow, which has Keras as a sub-module. And now let us just go through the steps. So here in this part, I'm building my network that has 3 input neurons. It then has a first layer of 5 neurons. And then it has 2 output neurons. I don't actually remember why I used 2 output neurons. I would only need 1 here, but okay, that's how I started. And then, so this is already producing the network, so that's super easy as usual. So as usual, most of my time will be spent in producing these training examples. So this is my function that I call produce batch. Of course, I need to know what's the batch size and what's the number of time steps. And so now I will produce 2 arrays. One consists of the observations. These are the inputs. So how many are there? Well, first of all, it's a full batch. Each piece of the batch consists of a number of time steps. And each time step has 3 values, 3 neuron values. And then there's the desired output. Again, there's the batch size, there's the number of time steps, and at each time step maybe I have these 2 outputs. And so now I want to randomize things. So for example, I want to pick a random position at which I tell the network what I expect it to memorize. And then I will also produce a random position that is later where I ask the network what it has memorized. And so these I simply obtain by drawing random integers. And I draw not only one random integer, but actually as many as my batch size requires. And this little calculation here just means the position at which I want to tell what I wanted to memorize will lie in the first half of the total number of time steps. That makes sense, because then in the second half I will ask it to give the result. Okay. And so now you remember from what I said before, input neuron 0 should carry a 1 at the position where I want to tell my network what it should memorize. That's the signal, so to speak. So what I want to do is I want to take my observations array, and I want to, for each of the example trajectories, for each of the example time traces in my batch, I want to set only one particular time step to 1, namely where I want to tell it. And that's at the tell position. Now, if that were a single number, you immediately understand the syntax of what I'm doing here. But it's not a single number. Remember, it's a full batch. It's an array of size batch size. And so Python has this nice syntax where I can actually, in a single go, instead of doing a for loop over the batch size, I can set all these array entries to 1. So this is equivalent to looping over the batch and using the entry of tell position for each batch entry in order to set the corresponding time slot to 1. But this is just more efficient. In the last line, I will set the neuron value number 2, the value of the input neuron number 2, to 1 at what I call the ask position, when I want to ask the network what to do. And again, I use the same trick in order to avoid a for loop. And then I still want to produce those numbers that the network should memorize. So again, I produce a random batch of numbers, and I store all these numbers at the appropriate positions, namely always at the tell position, yeah, where I also give the signal. So if you are unfamiliar with this, I encourage you to look into how NumPy deals with arrays, because this is a very efficient way to deal with it. Okay. So say I have a batch maybe of 100 or so. I don't need to have a for loop over 100 entries. I just do it like this. Okay. But anyway, this is how I produce my batch. And then I still have to calculate what is my desired output. That's a time trace that corresponds to what the network should produce. And it should only produce a single value, a single non-zero value, that is at this ask position when it is asked what was the number that it memorized. Okay. And so then I return both the input and the output, and that is what we will use for training. So again, as usual, producing this training batch is the most elaborate part in such a program. Fine. And so now let's run this. So what I'm doing here is, well, I set my parameters. I initialize my network. And later I run through all the epochs of my training. I produce the batch. I train on the batch. And then I also want to see how my network progresses and becomes better. I could simply plot the cost function, and it goes down, of course. But what I often like to do is I want to produce one time trace, one input time trace in this case, that serves as my test case. It's a time trace that the network is never trained on, but it's my test case that I will repeatedly ask the network what is the answer for this test case. So after each training step, I will ask the network again, okay, what's your answer for this test case? And that will give me a visualization of how the training progresses. So let's just run this. I will run for 1,000 training epochs with a batch size of 20. So in total there will be 20,000 time traces. So at the end of the training, my network has seen 20,000 time traces, and for each of them it has been told what should have been the correct answer. And so the weights have been updated. We are halfway through. The output is a bit scrambled, but never mind. You see the deviations, so to speak, the cost function goes down. That's good. Okay, so we are finished. And now I can plot the result for this particular test trace. So apparently so I have to explain how this figure looks like. To the right, I have the training epochs. So it runs up to 1,000. And on the vertical axis, I have the time. Yeah? So I think it runs up to 20 because this is the number of time steps that I had. And so the color scale just displays the values of the output neurons of the network. And so after each training epoch, I ask it again for the particular time trace, for one particular test time trace, what's your output? And initially, as you can see, if you look at these early training times, the output is completely zero. So it's just dark blue. So it doesn't give any output. But then, since it's been seeing many example outputs that are correct, it starts to figure out things, and eventually it latches onto the correct behavior. So eventually, at one particular time slot, that is the time slot where I really ask it to produce the output, it will give me the correct answer, which in this particular example was 0.7, but that of course has no meaning. This is only the particular test example. Yeah? But again, I want to remind you, it has never been trained on this particular test trace. It has been trained on many other traces, and from those it has learned how to generate the correct answers in general. And this is one example. Yeah? So now if I tell it, please remember the number 0.7 and at time step, I don't know, 17, I tell it, please now, what was the number? It will spit out 0.7. Yeah. So this is a nice way in general of testing the behavior of neural networks. You keep one validation example and then you visualize it. Yeah, so this is the input to the network. So at the first time step, it's just all 0, 0, 0. And then already at the second time step for this particular example, the first neuron is 1, indicating, oh, now please pay attention. And then the second neuron is, it happens to be 0.76. This is the value that it should memorize. And then much, much later, near the end of the time evolution, the third neuron has been set to 1, which is the signal that now, please, I want to get back what I stored in the memory. And it works, as we can see nicely in this plot. Okay, here's another little quick test. What I'm doing here is I take a full batch of, I think, 30, and I'm plotting what would have been the correct answer, that's the upper plot, and I'm also showing what is the actual answer. So time runs to the right, batch index runs on the vertical, the color represents the output value, and if everything were perfect, the target picture and the output picture, they would be completely identical. Now they are not completely identical, yeah, so it's not yet perfect, but it's mostly correct. So you see that it gives these outputs at the correct point in time. Okay. So now, is there a question about this example? You can also now play around in different ways, which I did here. Maybe I shouldn't go through all the details, but you can try, as usual, you have trained your network on a set of examples, and it should be pretty good for anything that resembles these examples. But now what will happen if you ask it on a completely different example where you changed something qualitatively? And so what I decided to do here is, instead of just asking it once, what's the value that you memorized, I will ask it twice. And so at least qualitatively this is different from what it has been trained on. The question is whether it still gives the expected behavior or not. And as you can see here, so in each of these time traces there are now 2 times in which a value would be expected. And as you can see here, luckily it even reproduces values now in 2 time slots. So this is not something that is guaranteed, because I don't know what's behind the scenes, so to speak, what is its internal mechanism, but at least apparently here it worked. Yeah, there was a question. Yeah, that's true. The values themselves are not so great. So you're pointing out, okay, so the expected traces range from 0 to 1 versus the actual outputs, they don't exploit this full range. Okay, so I'm not completely certain about, I think the random numbers were pulled between 0 and 1. So what can really happen is, as we're getting closer to the range of values that it has seen, then of course the approximation becomes worse, because somehow these come very rarely, so it is not punished so much if it gets things wrong near the end of the range of the values. So I'm guessing this is the reason. And so maybe if in your final application, whatever it is, you have a certain range of values, maybe you want to make sure that maybe you want to train even beyond this range of values if it's possible. Okay, so let me go on to the next example. This is a network that counts down. So again, this is of course just a toy example, but these are ingredients that will also appear in more sophisticated examples. And so you could imagine that, again, maybe now I have 2 input neurons. One of them, again, is a signal that it now should pay attention. And it should pay attention to the value in the second neuron, which here I take to be 7. And now the meaning of this value is something that I define by my training examples. And the meaning will be that after 7 time steps, I expect it to output a 1. Yeah? So the meaning of this extra value is just, please now, starting from this point in time, count down 7 steps and then give an output signal. And again, in order to make it work, I will produce many such example sequences with many different values and many different points in time. And then you will get your output. So you hear a thunderstorm. Maybe there would be an interesting application for an LSTM network to try to listen, I don't know, to the thunder, and then maybe try to predict what is the distance, which you can also measure independently from the flash, because maybe if the thunder is close by, it will have a more crackling noise. I don't know. So that's just made up. Okay. I think I produced somewhere a network that counts down. Yeah, so this actually also works after quite a bit of training. Here again, you see this depicted in the same version that I had before. Training epochs run to the right, time runs to the top. And here I needed about 1,000 training epochs until finally it started to converge to the right behavior. Yeah. Again, as usual with neural networks, it's a little bit hard to predict what will be easy and what will be hard for the neural network. And now of course, these are very constructed toy model examples, but the fun thing is that there are in more sophisticated examples, these are ingredients that occur automatically. It starts to count down something, it starts to switch on and switch off when it encounters certain input signals and so on. Okay, so this we already had a look at. This we also briefly mentioned the countdown network as it progresses during training. Now, here's another example. So one of the obvious applications of time traces is when the time trace is actually a sequence of characters, a sequence of letters. So it represents a text. And one of the things you could ask for is, well, given a certain piece of text, can you predict for me what's the likelihood to have one or the other letter as the next letter in the sequence? So for example, here, just imagine that this is the input sequence. It says the space theory space of space GE. And that's what the network has seen so far. And now you will ask the network, what do you think is the next letter? And your neural networks should be able to guess what is the next letter. Of course, it's not properly defined. There are multiple possible solutions. But if you've been reading a lot of physics texts, the most likely solution is that the next letter is an N, because maybe it's the theory of general relativity. But then again, if you're in medicine, maybe there's another possible solution. Yeah? And more generally speaking, we want the network not just to output a particular letter, but really a full probability distribution of expected next letters, something like this. So you would have the full alphabet, and then you would maybe say, oh, with highest probability, this letter can come as the next letter, and then you have slightly lower probabilities for other characters, for other letters. More technically speaking, the way you would encode the inputs would be that each letter could be represented in this one hot encoding that we already talked about. So there's actually not one input neuron, but for each letter in the alphabet there would be one input neuron. and one of them you set to 1, corresponding to the letter that you actually observe. And so you have multiple input neurons for each time step, and also you have multiple output neurons carrying the probabilities, the predicted probabilities for the next letter. So input is one hot, output is a probability distribution. And so you can train this on really large amounts of text and ask that the observed probability distribution is matched by the network, which you can do by a categorical entropy kind of cost function easily. And then let's see what happens. So there's a wonderful blog entry by Andrei Karpathy about the unreasonable effectiveness of recurrent neural networks. And so what he shows is that you can directly train these kinds of networks on megabytes of text. So you always feed in letter by letter the text, and you know from your text database what should be the next letter, and that is the desired output that you demand from your LSTM. And then in the beginning it just produces rubbish. So the way how these texts have been produced is a little bit similar to my test case example. So you may start with some letters, you put them as input to the neural network, you get a probability distribution for what would be the next letter. Then according to this probability distribution you sample something. So if N is the most likely letter, then with a high probability it will be an N, but maybe it could also be an E if that has a good probability. Yeah? So you sample from this probability distribution, that produces you the next letter, that extends your sequence by 1, then you feed, then this whole sequence again acts as input to the neural network, again it produces a probability distribution for the next letter, you sample from this probability, you produce a letter, and so on and so on and so on. So just by giving a few first letters, afterwards you let the network completely fantasize something according to the probability distribution, according to its understanding that it has gained after having been trained on these megabytes of text. Yeah? And so now here on this page we have collected several examples in various stages of the training. So at first it's complete rubbish, so it hasn't understood anything, except maybe that sometimes there's a space. So you see spaces come relatively often. And also you see, for example, the letter E comes relatively often. That's because in the English language in particular, the letter E is a relatively frequent letter. So at least it has understood the, so to speak, the probability of having different letters of the English alphabet. If you pick a random letter in a big text, what's the probability of having an E? Probably on this level it has already understood something. But then, of course, there will be correlations between letters. If the last few letters had a certain values, maybe the next letter, the probabilities should change depending on that. And so here now you see not even real words, but it sort of gets better. And then at some point, it can output reasonable words. Not all of them are reasonable. Some have still typos, but many of them you can already recognize. And I remind you, it has only learned on the level of character by character, only single letters. So these words come about because once you start with W-A-L, and then you try to guess what is the next letter, then by all the training examples it has seen, it will guess the next letter is also an L. Because in these training examples, when the three letters W-A-L came together, very likely it was actually part of the word wall, and so the next letter is an L. So that's the way it argues. And then it becomes better and better, and here it's already sentences nicely, even with quotes, yeah? So it learns that it can start a quote, then blah, 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 and then it should have an end quote. It learns the structure of the text. It even learns that the comma is sitting inside the quote. And you can tell me which text this was trained on. No? Okay, think about it. That's a good recognition task for your neural network. Anyone guessing? I'm not sure myself, but I guess from the names. I believe it's War and Peace, yeah? Because there's Pierre and Natasha and so on, yeah? But I'm not sure. Okay. So you can have more of that on the internet with the works of Shakespeare and so on. They have trained it also, so for example on the Linux kernel, so on the source code, and then it starts to produce examples, of this kind, but writing source code. And it even has been trained on the LaTeX code of mathematical papers, and it starts to write proofs on its own. Of course, these proofs don't make any sense, but it has learned to say things like proof omitted for brevity or something like this. Okay, so it's big fun. So Google the name of Andrej Karpathy and this blog. And here's another homework just to illustrate what things you can do as a slightly more sophisticated example. You could do the following. Let your input be, again, a sequence of letters, but these letters are now mostly numbers and maybe some algebraic signs like plus. And something like 3 + 5 equals, and then maybe question mark. And the output should be the result of this calculation, yeah? So you're putting in a request for an algebraic calculation letter by letter, and the network must now learn to memorize, first to memorize these numbers, then also to convert these, what had been simple characters, to convert them internally into a real number, to produce the sum of those and output the sum. Yeah? And it's interesting to see how good it becomes in this. And then if you're really smart, you can also try to analyze the internal structure of the network, what it tries to do. And obviously, it's a little bit different if these numbers are just short, just one digit. Maybe then it can even memorize the result. Yeah, this is also what we do in school at first. But you could try whether you can make it work that these numbers become longer. Then it cannot possibly memorize everything. Then it really has to come up with the correct algorithm for adding up these longer numbers. And we know there are such algorithms, but then the question would be, does it rediscover the same algorithm that we know, or does it do a different algorithm? Okay. So are there still questions about these recurrent neural networks? So they are real fun. Okay, so obviously they are very important because time traces are all around. Now I want to switch to something that still has to do with these recurrent neural networks, and it also has to do with pieces of text. But now we will not talk about individual letters or characters anymore. We will talk about whole words. And now if you're dealing, if you want to split a text into words instead of characters, and you want to represent this as input to your neural network, the simplest encoding would again be a one-hot encoding, where you say, my vocabulary has 1,000 words, so I have 1,000 input neurons, and if I pick word number 35, then the input neuron 35 would have 1 and the others would be 0. So I depicted the situation here. These would all be your input neurons. Each of them corresponds to one single word. And then if the word that is currently in your story that you are reading happens to be warm, then you want to put a 1 there. But of course, this way you need a lot of input neurons. So the dimension is really the number of words in your dictionary. And 1,000 is a very restricted dictionary. So maybe to read more sophisticated things, you need many more words. So this is one problem with this, that you need a lot of input neurons because there are so many words in the dictionary. Another problem sort of is the position of these words in this list, or the whole input vector, so to speak, has no semantic meaning yet. I mean, we have probably, I don't know, we could take the whole dictionary, order it alphabetically, and then write down all the words in alphabetical order, and then that would be the order in which our input neurons are assigned. But it would have no particular relation to the actual meaning of these words. Yeah. It would be much better if, first of all, we could compress these words into much smaller vectors with a lower dimension. And second, if the placement of these vectors in this still large dimensional space had any relation to their actual meaning. And so that's the idea behind this concept of word vectors that was invented a few years ago. So, for example, each of these words now would no longer be a one-hot encoding. Instead, it would be a real vector that has non-zero values for many of the neurons. Yeah? And then if you were to plot the endpoints of these vectors in your high-dimensional space, of course I only can plot it in two-dimensional space here, then you would want to arrange it, or you would want to have an encoding such that, for example, words that are related to temperature are relatively close together. Yeah? More precisely, there are, of course, many dimensions to these vectors, and you would hope that with respect to some dimensions, words that have something to do with temperature are close together. Yeah? And then there would be other dimensions of these vectors that have a different semantic meaning. For example, I don't know, something that can be used as a noun has a different value with respect to this other dimension. That's something that would be a verb, and so on and so on. So you hope to get an encoding that has more meaning than the simple one-hot encoding. And so the question is, how do you get there? How do you know what is the meaning of a word? And so in the 80s, or since the 80s there, and even earlier, there were attempts to encode this by hand. So you would have experts that tell the computer what's the relation between different words. It would say things like Paris is the capital of France, Rome is the capital of Italy, and all of this would be hand-coded as relations between words. And the idea is, after a while, you get a large database that has all this knowledge about the world encoded. But now here the approach will be very, very different. The approach is this brute force big data approach, yeah, that we already saw with the megabytes of text that were fed into the neural network for this letter-by-letter prediction. So here you would feed text, but now on the word level, into a program, into your neural network, and you would want it to learn on its own. It should guess on its own from what it sees whether some words are related or not. Now, how do you do this? It's completely unclear at first sight. And therefore, it's very surprising, the very simple-minded technique that people came up with. They say, oh, probably two words are related if they appear close together. That's, of course, very, very simple-minded, but it works surprisingly well. Yeah? And so here I just briefly flash the very original idea, but then I will go on to how it's done today. So the original idea was take a word out of your long text at time t. So with time, I just mean you number the words in your long text. So then that's t. Take the word, map it, try to map it to some internal representation that is of smaller size and represents these word vectors, and try to predict from this representation the next word that will come in the text. It's a little bit similar to what we did letter by letter, but now it would be word by word. And so you would get as output a probability distribution in terms of the words in the vocabulary. So it would tell you not what is the likelihood of different letters appearing as the next letter, but now what's the likelihood of different words appearing as the next word. And the idea was that if this internal representation is chosen well, this network would be doing well in predicting the likelihood of the next word. So there's a problem with this, namely that you need to have a probability distribution over all possible words in your dictionary. And your dictionary may have 10,000 words or something. So it will be a really long, really big probability distribution. So really a lot of output neurons. So this is no longer the way it's done, but this is how it started. And so there's now an alternative, which is what is done nowadays. So what you do nowadays is, on the one hand, you tell the network what would have been the correct next word. You know this, you just look at the text. And then you provide it with a few fake examples, words that are just random words. And then you want it to be able to distinguish between the true next word and these fake next words. And so then the network doesn't need to output a full probability distribution, just needs to discriminate between the words. And even then there are a little bit different approaches. So either you can give it the context of words, for example, the surrounding words, and it should be able to kind of guess what's the, or determine whether another given word is the correct word you're asking for or not. Or you can take the given word and have it try to guess what are the context words. So just to make it clear, here's a typical example sentence. For each of the words in the sentence, you could look at the context words, which could just be the surrounding words. And then the network should be able to discover whether a given word is a true context word or not. Okay. So here's an example how it really works. So, for example, given the context word age, for example, the last word, the most recently encountered word, the network should tell us what's the probability that W is the correct word. And well, this is how this could be represented. And now at each time step, you want to go down the gradient of a cost function, and this cost function is such that on the one hand, you stick in the correct word that you know is the correct word, and on the other hand, you just take a few noisy examples that are probably not the correct words. And then it should be able to distinguish between the two and make this cost function small, which just means this probability should turn out to be large, those probabilities should turn out to be small. And so this is now different from what we had before. So before, given some context, we wanted the network to spit out a full probability distribution over all the 10,000 words in the dictionary, and that is a little bit cumbersome. Here we just give both the context word and the presumed word that we're talking about, and it just should tell us whether this is whether the word is true or it's fake. Yeah? So the output of the neural network is just a number between 0 and 1. This is much easier. Okay. And so now a few results, and it's really amazing. So if you plot things in the right way, it turns out that, for example, the word car will be here, and in its relatively close vicinity will be the word cars, so the plural. That's already nice if they somehow are grouped together. But it's even more amazing that now if you have tree and trees, of course the tree sits somewhere in a very different part of vector space. But the distance between tree and trees, this vector that goes from tree to trees, is almost the same as the vector that goes from car to cars. So suddenly you have discovered a vector that takes you from the singular of a word to the plural of a word. Just by having this large training database of many words and always seeing which ones come together. And it gets better. So for example, it can discover how to change the gender of a word. It can learn to go from man to woman, and then the same vector can be used to go from uncle to aunt or king to queen. So that's really amazing. Yeah? So you suddenly can do algebraic operations with words. And so when people discuss this, they really write down equations like king plus woman minus man and then you get a vector. And then, of course, this vector will not be precisely the vector for queen, but if you look for the closest vector, it's very likely that queen will be the closest vector. Okay, and here's another example that's from this paper. Here you see different countries, and here you see different capitals, and you see the vector connecting the country to the capital in this way of drawing the coordinates is a mostly horizontal vector. And so you could then try to guess by adding to Germany this kind of vector, hopefully you end up with Berlin. Now you might say maybe this doesn't work so well because here, for example, when I add this vector to Greece, maybe I don't end up with Athens, but I end up down here. But remember, there are also many, many different dimensions that are not plotted here. So even if in this projection things seem close together, they need not actually be close together. And so that means even for these cases where it seems a little bit doubtful, you can still end up with the right result. Okay. And so again, I want to advertise it a little bit. These, yeah, there's a question, please.
Those PCA inputs are usually done with the two biggest eigenvalues, right? Or is there some bias in the dimensions?
Yeah, I'm assuming these were the biggest eigenvectors simply. Yes. Mm-hmm. They just needed a way to, I mean, you have to choose some coordinate system. Okay, so now you don't need to program this yourself, even though it's only a few years old. Keras has this done for you. So if you want to go from a dictionary of words of length word index to some word vectors of some embedding dimension, here's the whole thing that you need to introduce into your neural network. Yeah? So, and then there are many other classes that help you with the pre-processing of the text and so on. But then again, it can still be a relatively large effort to actually do the training because you have to go through large databases, you have to train for a long time. And so others have done this for you. And you can search for such word embedding databases. And for example, they have been trained on the English version of the Wikipedia. And so at least these word vectors represent the world according to Wikipedia somehow. Yeah. Okay. Well, are there still questions about word vectors? So I suggest really you Google these word vectors. There are these large databases. It's really fun to play around with. Also, you Google the example with the recurrent neural networks letter by letter. It's really fun to see this also done for other cases. And the programs you can download, and then you can run this on your own texts and see the kind of funny texts that result. Okay, very good. So then I at least want to start already this lecture, a rather advanced topic. And that, I believe, goes back to something that I mentioned in the beginning as one of the spectacular examples of neural networks. And that is called reinforcement learning. So we already talked a little bit about unsupervised learning, at least in the sense that there are these techniques like TSNE that can give you kind of clusters of things that seem to be similar. But most of the time we've talked about supervised learning. So you give a lot of training examples, you give the input and the correct output, you give this 10,000 times, and eventually, hopefully, the network becomes smart enough to generalize this and give the correct output itself. But this way, it's very hard to ever go to a really artificial intelligent system, because basically you have to put in what you want to get out. And so the situation changes with reinforcement learning. So this will be a situation where although you still know what you want the network to achieve in the end, you know what will be rewarded and what is good and what is bad, you don't know what should be the good strategy to achieve this end. You're not really like a teacher who knows how to do things. You're just like a customer who knows whether what you give him is good or bad. So this is reinforcement learning. So let me first talk about the general setting. So reinforcement learning is something that comes up in many very important applications, including robotics and self-driving cars. Also, it has been applied recently to many kinds of different games because they provide a nice test case. And the setting is this. You have an agent, you can think of a robot, and you have an environment, which is just the world around the robot. And so now this agent can do actions, like it can move around or it can grab something. And these actions will, of course, influence the environment, for example, because it drops an object or it moves something or it moves its own body somewhere else. And then, during each time step, it will also observe the world around it. And these observations hopefully help it to take the next action. So based on these observations, it has to decide what to do next. Now again, there are many interesting distinctions here. It could be that the agent has a complete observation of the whole environment. Think of it knows the whole map of the world, it knows where every object is. This is a situation you might have in a computer game. Or maybe, and this is more realistic in real world, it only partially observes its environment. It only sees the immediate vicinity and not much more. And so just to make clear what are the typical settings, for example, for a game, you could observe the whole game board and then you have to place a stone somewhere. Or you observe the video screen of a video game and you have to move around in this video game. But the challenge is, as I said before, you don't really have a teacher who knows what is the correct action. No one tells you what is the correct action. So therefore, there is no supervised learning. And the question is what you do. Now, of course, there must be something that tells you whether you're doing something right or wrong, because otherwise, how do you even know where you want to go? And so there will be something that is called a reward. So you get a reward if you do something right, but maybe not instantaneously, maybe only at the very end. Think of a game. At the very end of the game, you are told whether you have won or lost. So this is the only time when you get a reward. But of course, what determines whether you have won or lost will be all the moves you took before. So this makes this so challenging. So that is the domain of reinforcement learning. You want to train a network to tell us which actions to take, but not based on training it on the correct actions. It is not being told what are the correct actions. It's only based on these very rare rewards. And so there's a challenge in this, an intrinsic challenge if you think about it. So in the end, we again want to use this concept of a cost function, or the reward is maybe the opposite sign, so something like a negative cost function. We want to make this reward as large as possible, and as I will show you, we even want to do something like gradient descent, because we don't know much more. This is our, this is the tool that we have available. But now, if I'm being told at the end of the time sequence whether I won or lost my game, or whether I achieved my goal in my environment or not, if I now want to do gradient descent, the problem is that sure, I can do gradient descent on trying to update the predictions for the actions, so in order to try to modify the actions that I would have taken. But this gradient, if you do it naively, would also mean taking the gradient of what the environment does, because in reaction to every action you do, the environment does something. And now if you ask me, how could I have achieved a better reward? I might have to answer the question, well, if I had taken the other action, then the environment would have reacted differently, and that would have resulted in a different reward down the line. So in this case, you would need to predict the different response of the environment if I had taken a different action. But in many cases, we don't know. It's not that the environment is usually given as a set of differential equation and then I could imagine, okay, if I had moved a little bit to the right, let me calculate what that would mean for the trajectory of the environment, which I could do in such a case. But no, the environment is maybe just like for a robot, it's the real life environment. I have done just a sequence of actions, I get a reward. I think the reward is not very great. What could I have done differently? But I don't know how the environment would have reacted in a different situation. So this is a problem. We often don't have a model of the environment. And so what we will be talking about here will be so-called model-free reinforcement learning, when I don't need to have such a model of the environment. I don't need to be able to answer the question, if I had done a different action, what would the different response of the environment have been? And it's amazing that this works, actually. Okay. Now I want to make this a little bit more concrete. So here, this is like a little game. We have a player who's moving around, and whenever the player comes across one of these green circles, that's a kind of treasure chest that it can collect, so then it gets a reward. And even for the simple case, there are many ways of precisely defining the scenario. For example, you could say the state that you observe is the full map. So at each point in time, the player can observe this full map of green and red dots, so to speak. It could also be that the player only knows about its x and y coordinate and doesn't even observe where the boxes are, where these treasures are. So there are even different scenarios now for what is the state that the player has access to, what it can that it can observe. Now the actions are the different moves, maybe up, down, left, right. And then the reward will be based on how many treasures you have collected. And your goal is, of course, to collect as many treasures as possible. And then again, you can distinguish different games. Maybe these treasures always sit at the same points. And if you play the game long enough, you can memorize where are these points. Or maybe whenever you start the game again, the treasures sit at different points. And maybe you have to figure out where they are sitting. Okay. And so I now want to start discussing one of the earliest reinforcement learning techniques that are model-free. And it's called policy gradient, or at the time it was called reinforce. So how do we get around this problem that we cannot answer this question, what would the environment have done if we had chosen a different action? And it turns out the way to go about this is to use a probabilistic action choice. So our network, or whatever it is, will not give us deterministically what is the next action to be taken. It just gives us probabilities for different actions. And that is good on many levels. I will tell you in a moment how it solves this problem with having to model the environment, which we don't have a model of. But there's another much more obvious advantage. It's that if you have probabilities as output, probabilities are a smooth function. They can be thought of as a smooth function. They are continuous. So now if you want to start thinking in terms of gradient descent, you can imagine that you adapt these probabilities only a little bit in each learning step. So that's already good. It makes things more smooth. And the question is, how do you decide which actions you make more likely? For which actions should you increase the probability? Ideally, these should be the actions that have contributed to a large reward. But how do you know which actions have contributed to a large reward? And so this is actually not what is being done. It's not that the network somehow figures out, oh yes, this was a really good action and that was a bad action. Rather, what is done is the following. You just run this, what is so-called policy, so you do whatever your strategy is with the present network, with the present probabilities. And in the end, you get a reward. And then if the reward is high, you say, oh, that's good, I must have done something right. And then you decide to increase the probabilities of all the actions that you ever took during this sequence. Every action, no matter what. This sounds a little bit funny because among these actions there will probably also be some actions that were not very smart. Yeah? You ended up with a high reward, but maybe action number 3 was a really stupid move, but it was somehow overcompensated by the actions after that. Yeah? Still, all these actions get rewarded, their likelihood gets increased. So sometimes you even reinforce bad actions, but the good thing is, when actions are really bad, they will more likely occur together with a low reward than with a high reward, because they are so bad. So that means if you run through many training examples, many trajectories, then it's more likely that the really good actions will get pushed up in probability, because the not so good actions, they will more likely occur together with a low reward, and then they will be diminished in probability. So that's the idea with this policy gradient. And I think maybe that's enough for today. Maybe let's discuss the technical parts then next time, which is this Wednesday actually already. Are there questions at this point on the qualitative level? Well, if not, then see you next time.